All right, guys, can I get a thumbs up at home that you hear me and see the board okay? All right, here we go, guys. This is it. This is the last section. This is section 7.4 on trigonometric identities, which I've already shown you the identities, these statements of equivalence. We're just going to be able to use them now to simplify trigonometric expressions or to verify that something is actually true and equivalent, okay? So when you are dealing with an identity, it says two functions f and g are identically equal if f of x equals g of x for every value of x for which both functions are defined. Such an equation is called an identity. So guys, for example, if you have the expression 2x plus 5, and I simplified that by distributing to 2x plus 10, either way I write that expression, it's equivalent. So no matter what I plug in for x, the left side of this equation is going to equal the right side. So that's in identity. All right, here we have the equation of the unit circle. So it says cosine squared theta plus sine squared theta equals 1. No matter what angle I plug in for theta, when I add them up, it's going to equal 1. It is going to be true for any angle that I plug in for theta. Those are identities, okay? And then you have what we call an equation that is not an identity, is just called a conditional equation. So guys, the equation 3x plus 1 equals 10, that's only true if x equals 9. So you can't say that that's an identity. The left side only equals 10 when x is 9, where this left side will equal that right side. No matter what number you plug in for x, it's going to be true. So you're able to use these identities as a way to rewrite something in an equivalent way. A lot of times the identities are used to simplify a trigonometric expression down to something that is more simple to use. It's able to take, if there are different trig functions involved in one expression or equation, then I can use an identity to maybe rewrite it in terms of just one trig function. So the identities are very important and you use them in calculus a lot, all right? So trigonometric identities are statements of equality that are going to allow us to rewrite one trig function in terms of another trig function. Guys, I've already defined these back in, I think, chapter 6 when we first saw the identities. So instead of me just reading them all out, just look over them. These should all ring a bell. I've written the Pythagorean ones down here. Those are all the ones that involve the sine squared functions and whatnot. And then don't forget, you even have your even and odd identities, right? Odd functions, even functions, and more odd functions. Just a way to get that negative sign out of the input, okay? All right. The goal in this section is to establish new identities by algebraically manipulating trig expressions. So guys, if you ask me, it just puts your algebra skills to the test. This is all about the algebra. All right? Some techniques do this will be demonstrated in the following example. So guys, here's some things they're going to ask you to do. Let me just move it up so you can see it. So when you are working with these trigonometric expressions and you're using these identities to simplify them or rewrite them in an equivalent way, some techniques that we're going to use are rewriting a trig expression in terms of sine and cosine only. That's a big one. A lot of times when you're working with a trig function or a trig identity, a lot of times your goal is just to rewrite everything in terms of sines and cosines and see what cancels out. Another technique is going to be multiplying the numerator and denominator of a ratio, a fraction, by a well-chosen value of 1. So guys, what that means is kind of think like conjugates. Remember if you were given this expression 3 divided by 5 plus root 7? Normally we don't leave irrational expressions in our denominator, so we would multiply it by its conjugate on top and bottom. Well guys, guess what? This that we multiply top and bottom by is 1. It's a well-chosen value of 1. So a lot of times in that technique, you're multiplying by probably some type of conjugate, which is a well-chosen version of 1. All right? Then you're going to have writing sums of trig ratios or fractions as a single ratio. Guys, that's basically just adding and subtracting fractions and making them become one fraction. So you'll have to get a common denominator and make these two ratios become one ratio. All right, and then the last one, factoring. Don't forget factoring techniques. We look for GCF. Difference of two squares is a big one. You have all these Pythagorean identities now that have these squared trig functions. So the difference of two squares pops up a lot. So look to factor that. And then I added a fifth one. The old pre-calc book, which was actually my pre-calc book in high school, we only got this new book like 4 years ago. The old pre-calc book always had a fifth method that we use, and that would be to cross-multiply. If they're going to give you some type of established identity, then sometimes cross-multiplying is an easier way to go because it helps you to avoid complex fractions. Fractions within fractions, because these can get a little bit messy, all right? Our book doesn't really have you do that. It usually just goes with, I believe, the well-chosen value of 1, but sometimes I'm telling you, cross-multiplying makes the problem a little bit more simple. All right, these are all techniques that we could use. So let's go to an example and let's try one. All right, I think I'll have enough room. This is all right, so guys, they said simplify cotangent theta divided by cosecant theta by rewriting each trig function in terms of sine and cosine. So again, this is a big one. A lot of times your goal is, if you're ever looking at an identity, you're like, I don't know what to do. And sometimes the best place to start is, let's just start writing things in terms of sines and cosines. So if we rewrite this in terms of sines and cosines, can we make it become something more simple? So guys, cotangent theta is actually cosine theta divided by sine theta, right? It's the reciprocal of tangent, and tangent by definition is sine over cosine, right? And then it's divided by cosecant theta. Cosecant theta is the reciprocal of sine, so it's 1 over the sine function. So you can see I have a complex fraction now. I have fractions within a fraction. So let's get rid of the complex fraction by multiplying by the reciprocal of the denominator, sine theta over 1. And then multiply the top by sine theta over 1. And now on bottom, everything's gone. I'm left with cosine theta over sine theta times sine theta over 1. Well, sine theta cancels with sine theta, and now I'm just left with cosine theta times 1 over 1, which is cosine theta. So guys, if you were given this problem, would you rather have to plug angles into this expression, or would you rather just plug it into that expression? So this is a much simpler equivalent expression to that. So that's what identities are trying to do. They're trying to lead you with something more simple and probably in terms of a better trig function. So now we know it's equal to that. So it's almost like just putting together a puzzle in a way. Everybody okay? All right, now again, the biggest thing I would feel as a student, I can remember sitting in pre-calc and feeling this way. I just feel like there's a lot it's a horrible feeling in this section of, all right, am I done? Did I do that right? It's kind of, it leaves you in a feeling where you're always unsure of whether or not you finished it correctly. And unfortunately, sometimes I can do a problem and still feel that way. All right, so just try and take it as far as you can. All right, let's look at number 2. They want us to show that this is equal to that by multiplying the numerator and denominator by 1 minus sine theta. So guys, they want me to show that cosine theta divided by 1 plus sine theta is equal to 1 minus sine theta divided by cosine theta. They want us to show that the left side equals the right side. Now, lucky for us, they've told us exactly what they want us to do in order to show that the left side is equal to the right side. They want us to multiply the numerator and the denominator by 1 minus sine theta. So guys, think of it as in a rationalizing sense, like when you rationalize the denominator and you use a conjugate. 1 minus sine theta is the conjugate to 1 plus sine theta. So we're going to work with this side, and we're going to try and make this side say what the right side is saying. So our goal is to leave this side alone. We're going to work with this side because that's the conjugate to that, to see if we can make this say that. All right, so leave that alone. Let's work with this. So let's multiply the numerator and the denominator of this side by 1 minus sine theta. So again, by multiplying the numerator and the denominator by 1 minus sine theta, it's literally a well-chosen value of 1. 1 minus sine theta over 1 minus sine theta is 1. Okay, well, I'm not going to be adding fractions together, so when I multiply my top, I'm not actually going to multiply them. I'm not going to distribute the cosine theta in, at least not yet. Let me see what it looks like just by saying they're being multiplied. So I'm just going to write 1 minus sine theta times cosine theta. That's going to be on top over. Now, guys, if these are conjugates, if you remember, multiplying conjugates is great because all the bad stuff cancels out, like the middle of that a plus b, a minus b, all that cancels out. So watch. I would get 1 times 1 is 1. Then I would get, don't write this down, I would get 1 times sine theta, it's a FOIL, is sine theta. And I would get minus sine theta times 1 is negative sine theta. Well, a positive sine theta and a negative sine theta would cancel, so that part's gone. And then I would just left be negative sine theta times positive sine theta is negative sine squared theta. So when you FOIL the bottom, because they're conjugates make that middle stuff all cancel out. All right, so guys, now we're going from here. So now it's like, all right, I'm trying to get this to say that. So I like that this is already in its numerator, but how do I get the cosine theta and this to become that cosine theta? What can I do? Well, guys, now think about your identities. Is there something you could substitute in that is equivalent? Anybody know who 1 minus sine squared theta is? He's one of our big Pythagorean identities. If you look at the front of your notes, what does 1 minus sine squared theta equal? Equals cosine squared theta. So we're going to be able to substitute this out. So now it's going to become 1 minus sine theta times cosine theta divided by cosine squared theta. And now what's going to happen to this cosine theta and one of these cosine thetas? They'll cancel, and I'll be left with 1 minus sine theta over just cosine theta, which is exactly what I was trying to make this become in the first place. So now I have made the left side say the exact same thing as the right side. So sometimes, as weird as these problems can be, and again, you can definitely have that, oh, am I doing this right? Am I done? Am I, on the right track? I do like these problems in the sense that they're giving you something to aim for. You know you're trying to get one side of the equation to say the same thing as the other side of the equation. So it kind of gives you a goal. You know what you're heading towards equaling. So I like these ones because I feel like they always give me some type of direction. All right? Everybody okay? All right, let's go to the next example. Now, if I can just say this, it's not showing right now. If you go back to this exact same problem, this is the type of problem where our new textbook is a big fan of using this well-chosen value of 1, this conjugate, if you will. However, do you see how it's a ratio equals a ratio, a fraction equals a fraction? This is one of those problems where you could have cross-multiplied, and you actually will create a new statement of equality, and then you can just prove that the new left side is equal to the new right side, or vice versa. So this is one of the ones where if you go back and try it on your own, if you do it by cross-multiplying, it actually is an easier problem that way. But our book and the online homework is not a fan of showing you that technique, and I don't know why. But I'm telling you, if you have a minute, or if I have a minute at the end, maybe I'll put it on the filled-in notes. If you see this problem done by cross-multiplying, it's like 3 less steps, I feel like. It's like boom, boom, done. So it's kind of nice to remember that there is a cross-multiply option, even though I feel like our book doesn't show you. All right, now let's go to the next example. I will. I'll put that in the filled-in notes in case anybody wants to see what it looked like. Okay, this one says simplify this plus that by rewriting the expression as a single ratio. So guys, you're adding 2 fractions or 2 ratios, and they're asking you to simplify it by writing it as 1 ratio or 1 fraction. So basically, we got to add this together. We have to add fractions, and if we want to add fractions, we got to create a common denominator. So let me just rewrite it because I know it's hard to see. right, so let's add them together. So if we create a common denominator, what does this denominator need to look like that one? He needs a factor of cosine u. So we're going to time top and bottom of this fraction by cosine u. And then what does this denominator need a factor of to look like this denominator? It needs a factor of sine u. So we're going to times this top and bottom by sine u. Okay, now in the problem before this, I didn't actually multiply this out. I just said cosine u times that. I didn't multiply it out. Because guys, I wasn't adding fractions. I was just trying to show that the left side of the problem was equal to the right side. If I'm going to add these fractions together, remember, it's really just the top of a fraction that you actually add together, and then the common denominator stays the same. So if I'm going to add the top and the tops together, I'm going to have to multiply this out. I'm not going to be able to add that factor. So I am going to multiply this time. So this will be cosine u times 1 is cosine u, and then cosine u times sine u is just going to be positive cosine u sine u, over my new denominator of cosine u sine u. And then I'll be adding that with, what do I get on the other side? Same thing. I'm going to distribute my sine u to the top because I need to distribute in order to add the tops. So we'll distribute, and I'm going to get cotangent u sine u minus cosine u sine u all over my new denominator, cosine u sine u. Okay, so guys, now that we have a common denominator, I can go across and add my tops together. So I'd be looking for a cosine u to add together with another cosine u, but I don't have one, so that's going to stay cosine u. Then I have a positive cosine u sine u that I'm going to add with a negative cosine u sine u. They're going to cancel out. And then I'm going to have nothing on this side to add with that cotangent u sine u. I'm just going to have that positive cotangent u sine u. All over my common denominator of cosine u sine u. So again, this is where you get to a point like, all right, am I done? And that's where I just can't take away that feeling because I still have it to this day. I just look at it like, all right, I see my cosines and sines. That's usually a great thing. If you're in terms of cosines and sines, you're probably on the right track. But I see that cotangent, and I'm like, God, I know cotangent has a denominator of sine u. So the sine u on his denominator could cancel with the sine u in his numerator. So I think that's worth doing. So let's rewrite cotangent in terms of cosine and sine. So now it becomes cosine u plus, that's going to be cosine u divided by sine u times sine u divided by cosine u sine u. So now this sine u and that sine u can cancel, and I'm just left with a cosine u plus a cosine u. That's two cosine u's. They're like terms. Where right here, this is a multiply. Done. All right, so now I'm left with cosine u plus cosine u. That's 2 cosine u over cosine u sine u. Well, now I have no more adding and subtracting. I'm literally just multiplying and dividing. So now I can cancel the cosine u and the cosine u, and you are literally left with 2 over sine u. Okay? So that, guys, think about it. Would you rather have to plug angles into this expression, or would you rather plug them into this expression? This is a much simpler and equivalent expression to this one right here. Okay, now I have a little bit of an argument. I understand that a lot of times your goal is to get things in terms of sines and cosines, because they're like the main trig functions, if you will. Everything just comes off of a version of that. However, I look at this and I'm like, if I don't want to work with a fraction, I could go one step farther and I could rewrite this as 2 times cosecant u, because that's what 1 over sine u is. So to me, why wouldn't I want to work with that rather than that? And I get it, Because if you plug an angle into cosecant, you're turning it into a sine function anyway and reciprocating something. However, in terms of look-wise, this looks like a more simple answer than that one. So I feel like you could go back and forth and argue whether this is the finished answer or whether that is the finished answer. So I would accept either one on a quiz or a test. However, we know we're stuck to this online. Our book stops here. But I would never mark that wrong if somebody thought or saw to do that, okay? All right, let's see if we can do the last one, and then we'll stop there. I don't know if I erased anything too early, sorry. All right, the last one says simplify this expression by factoring. So again, they're giving you what they want you to do. They want you to factor. So guys, if they want you to factor, the first thing that comes into my mind in situations like this is difference of two squares and GCS. I feel like those are the ones that are going to pop up the most often. So guys, if you look at this, sine squared v minus 1, right? Think about it. If this was x squared minus 1, a simpler version of that, isn't that the difference of two squares? Doesn't that factor to x plus 1, x minus 1? It's a squared minus b squared. So it factors to a plus b and a minus b. Guys, sine squared v minus 1, those are two perfect squares. This is literally a squared minus b squared. You know what? Let me rewrite this because I know it's terrible to see. Okay, so this is literally the difference of two squares. So that's going to factor to a plus b and a minus b. So that's going to become a would just be sine v plus b would just be 1 times a, which is sine v, minus b, which is just 1. So that literally a squared minus b squared factors to a plus b and a minus b. Now when you go to the bottom, if you look at this one, I don't see any squared functions. However, this term has a tangent b, and that term has a tangent b. They have a factor of tangent b in common. Take it out into GCF. So now factor out tangent b. What would be left if I took a tangent b out of this term? Sine v. And then minus 1 if I took a tangent v out of that. And now what happens to a sine v minus 1 and a sine v minus 1? They cancel. And you're left with sine v plus 1 divided by tangent v. Now again, would you rather plug angles into this expression, or would you rather plug angles into this simplified equivalent expression? I'd rather work with this one. And they let you stop here. I have a little bit of a problem. I look at this like it's still a fraction, plugging angles in could still be complicated, so this tangent b is just staring me in the face. So I went a step further, and I rewrote this as sine v over cosine v, and then I got rid of the complex fraction. However, this is where our book stops, and that's where your homework is going to make you stop. However, I was not satisfied with that, and this is where I think we could argue, how do you know when you're done? It's a terrible feeling, guys. I still get it. So I went a few steps further, and I got this to become, I believe it was like cotangent v times cosecant v in just one expression. So to me, that was an easier expression to use, but our book didn't go that far. So again, it is up for interpretation a little bit, but this is where our book allowed you to stop. I'm going to show you how I kept going and got a different answer, but still equivalent in the written notes, just so you guys can see that. But this is where they told you to stop, which again, it's, I guess, to each their own, where they choose where you can and where you can't keep going, all right? And that's it. All right, so guys, I'm going to stop there. Hopefully you kind of get the gist of it, but you're just trying to make these expressions equivalent but more simplified. And then sometimes you're just trying to get them written in a different trig function. All right, do you guys feel okay? Yes? All right. So guys, I did create a homework on these types of problems. It's 7 questions, and I didn't make it due until Sunday night. There's literally no rush. This homework doesn't need to be done until we take our last quiz. So guys, I'm thinking maybe I can teach a little bit more tomorrow on these identities, and either I'll stop tomorrow or maybe teach again on Monday, but then that's it. I'm going to get the study plan up. I'm going to get the quiz up, and I might make it where next week seniors' grades have to be done by Thursday. So I might make it where maybe next week, depending on if I need Monday or not, you guys can just work on your study plan, which is literally almost non-existent if you don't want to do it. And then the quiz will be available. If you want to get done on Wednesday, get done on Wednesday. It's going to be everybody's choice. I'll try and leave it open probably to at least Friday. But seniors, I need your grades. So seniors are in a little bit of a pickle here, all right? But we'll talk more. But that's kind of my game plan as to how we can wrap all this up. All right, so at home, let me just quick take the attendance, and then you guys are going to be good to go.